Hello again. My name is Lewis McIntyre, and I'm here to talk to you today about constant acceleration in special relativity, using the velocity triangle to develop very simple graphical solutions that will explain why an unaccelerated observer will see acceleration decreasing as the velocity increases and conclude, therefore, that the mass is increasing. Let's see why that is. Unaccelerated velocity can only be determined with respect to some other body, and both bodies see each other themselves at rest with the other moving. Acceleration is absolute, unique to the accelerating body, the only one that can measure that acceleration with an accelerometer. This is proper acceleration. All other observers can only measure successive locations of that accelerating body to compute the acceleration. This is observed acceleration. We're going to deal with constant acceleration in this video. The accelerating body S0 is initially at rest and co-located with the observer S1 at time equal to 0. For every subsequent click of its proper clock dt, S0 will increase its velocity with respect to S1 by dv. For acceleration to be constant, a constant force F equal to S0's mass times its acceleration must be applied to the accelerating body in the direction of the x1 axis throughout the whole period of acceleration, and the body will feel a resisting inertial force in the negative x1 direction. This is what the accelerating body measures with its accelerometer. The unaccelerated observer cannot sense the acceleration of the body, but can only measure its displacement over time, differentiating once to determine S0's velocity with respect to S1, and once again to determine its acceleration. Now let's see what happens as S0's velocity with respect to S1 gets larger. We're going to use the timeline from the velocity triangle. At time 0, S0's timeline is initially at rest with and parallel to S1's at O. But with each tick of its clock dt sub 0, its timeline will bend by the amount d beta, equal to dv over c, with respect to its own previous direction. If the acceleration dv dt is constant, d beta dt equal to omega must also be constant. Thus, beginning at O, its timeline must follow a circular path of some radius rho in four-dimensional space. For acceleration to be constant, a constant centripetal force F must be applied normal to the timeline in the direction of the x1 axis throughout the acceleration, and the body will feel a resisting centrifugal force in the negative x1 direction. For small delta t, the delta v due to acceleration is very much less than the speed of light. Therefore, we can use the classical equations for circular motion. Using S0's proper velocity of the speed of light, c, as the tangential velocity of that rotary motion, we determine that the radius of the path rho equals c squared over a, almost a light year for 1 g of acceleration. Although this is linear acceleration of the body in its x direction, it is rotary acceleration in four-dimensional space. The centrifugal force is equal to and opposite to the centripetal force causing the acceleration, which reduces to F equal to mass times acceleration. It's interesting to note that we no longer have different rules for linear and rotary acceleration. All acceleration is rotary. In linear acceleration, the tangential velocity is the speed of light, the proper velocity of the accelerating body, and the rotation is in the xct plane. In spatial rotary acceleration in the xy plane, it is spiral rotary motion in xy-ct space. With respect to the CT timeline of the unaccelerated observer, and the spatial tangential velocity is just the sine component of the accelerating body's temporal velocity c. Otherwise, the rules are the same. Now let's see how our unaccelerated observer measures the accelerating S0. We're going to use the same methodology as we used with the unaccelerated velocity triangle. Light is emitted from event A at right angles to the S0 timeline to intercept the observer's timeline at B, then an equal distance along the S1 timeline to the observation at C. From this observation, S1 develops the measurement D, shown trigonometrically in terms of omega T0. What does S1's world line of accelerating S0 look like? S1's world line of S0 is located on a curvilinear path of successive measurements of the accelerating S0 by the unaccelerated observer S1. We determine the world line in terms of S1's coordinates x1 and ct1 using triangle OBE for one of these measurements to obtain the hyperbolic equation shown. Wikipedia gives a solution identical to mine, but with a much more arcane derivation and no graphics and very little explanation. This equation is called the Rindler hyperbola of constant acceleration, which we derive from simple graphical solution rather than calculus or tensors. Indeed, using the relativity polar plot, one can solve for the Rindler hyperbola without making any calculations at all, just using a plotter and divider. Missner, Thorne, and Wheeler, on page 166 of their weighty tome Gravitation, also came up with a similar equation after 2 pages of tensor calculus. This differs from mine in that they omitted C as they assigned it unity value and used a different offset. Mine used x1 equals 0 at ct1 equals 0, 0.0 on the chart, while in theirs it's at E. In high school, we learned that constant acceleration yields a trajectory x equals 1/2 at squared, which is a parabola. How do we square that with the hyperbolic world line? Let's step through the measurement of S0 and S1. At the beginning of acceleration, velocity is small with respect to c, the speed of light, and the measurement in the event are nearly identical. For such low speeds, we can use the small angle approximation that cosine omega t sub 0 is approximately 1, and that sine omega t sub 0 and tan omega t sub 0 are approximately omega t 0 in radians. In this case, the observed and measured acceleration and time are to a high degree identical, and velocity equals acceleration times time. Using the trig identity shown, we determine that x equals 1/2 of the acceleration multiplied by time squared. These are the classical equations for constant acceleration, the small angle approximation to the Rindler hyperbola. What happens as the velocity becomes greater? As acceleration continues, the velocities become significant with respect to that of light, and the measurement and the event become increasingly separated. We can take the differential of dx sub 1 with respect to dt sub 1 as shown, using the chain rule to express it in terms of dt sub 0. S1 will determine S0's velocity asymptotically tending to c, and the acceleration tending towards 0, as omega t sub 0 tends to 90 degrees. It is this diminishing acceleration that causes the apparent mass rise, because we cannot stop a moving body and weigh it. We determine the force acting on it and measure the resulting acceleration, and thus the observed relativistic mass, m at time 0 divided by cosine omega t sub 0, which is the relativistic radical. In a previous video, I demonstrated that the velocity triangle in the xct plane could be observed by a third observer, S2, receding in the y direction. The velocity triangle would map out parametrically in time on that observer's x sub 2, y sub 2 plane, converging on the exact representation as S2's velocity in the y direction with respect to S1 approach the speed of light. Let's see if the same procedure will work with rotational acceleration. To see the derivation of the spherical trigonometry math, please see my video number 5, Observing the Velocity Triangle, on this channel. Let's set the problem up. S1 in blue is the reference frame from which velocity in the x and y directions are measured. S1's timeline emerges from the sphere of proper time at A. S0 is the accelerating body in red, whose timeline is following the circular trajectory emerging from the sphere at B. S1 will observe S0 accelerating linearly in the x direction, following the hyperbolic trajectory in x over time we have just demonstrated. S2 in green is the observer who will see the rotational acceleration on his x2, y2 plane. We will see what S2 measures, first at a small velocity angle between it and S1, angle AOC, and again with AOC approaching 90 degrees. The instantaneous velocity angle between S2 and S0 is BOC. Alpha is the time-varying angle, ACB, between S2's measurement of S1 and of S0. S2's XY plane will be tangent to the sphere at C. Here we see that for any velocity in the y direction, S2 will begin to observe S0 following a curvilinear path shown in green on its XY plane at small velocities. The vector sum of S2's velocity with respect to S1 in the y direction and S0's velocity with respect to S1 in the x direction. The angle between S1's measured trajectory of S1 in the x2 direction and the chord line of S0's trajectory in the x2 and y2 directions will tend toward 90 degrees as the velocity goes to 0, along with angle AOC. This trajectory becomes more circular if S2's recessional velocity is near the speed of light, as its velocity with respect to S0 will tend to nearly the same velocity, and the angle between the measured trajectory of S1 and the chord of S0 in its x2, y2 plane will tend toward beta 10 equal to omega t sub 0 divided by 2. Here we see S2's calculated measurements with its velocity with respect to S1 at 25% of the speed of light in green, and at 99% of the speed of light in red. Rho is taken as 10, but it does not matter. Whatever the value of rho, the shape of the constant rotary acceleration will be the same. So in summary, the velocity triangle works as well with accelerated motion as it does with constant velocity, deriving graphically and with simple geometry a hyperbolic world line otherwise requiring some erudite math. And as we have shown, constant rotational acceleration is observable by some reference frame, indicating it is the underlying physical reality. This concept resolves any difference between linear acceleration, which is rotary motion in 4 dimensions, and rotary spatial acceleration, which is spiral acceleration in 4 dimensions. Please like this video. It helps YouTube to make this material more available to others. If you want to learn more, see my other videos on this channel or buy my book, Writing on a Light Beam. It's available on Amazon, or you can buy a signed copy through my website shown. And have a most enjoyable day.